Hello guys, we want to start lecture 40. So in this lecture, first I want to talk about Dirichlet problems, and then we talk about the superposition principle. Dirichlet problem is not something new, we already had it. So in fact, these type of problems, so they have some specific requirements. So for example, here you can see one Dirichlet problem based on a definition, a boundary value problem in which we seek a solution to an elliptic partial differential equation such as Laplace equation within a region R such that U takes prescribed values on the entire boundary of the region is called Dirichlet problem. For example, here we have a Dirichlet problem. Why? Because first we have a Laplace equation, and we know that Laplace equation is one elliptic partial differential equation. So that's why we meet the first requirement of Dirichlet problems. Second, we define this boundary value problem on a region R. So if I plotted, so we have x-axis, we have y-axis. X is between 0 to a, and y is between 0 to b. So as a result, we are solving this boundary value problem in a region that I show it here. So this region, it's R. The other requirement of the Dirichlet problem, so you should take prescribed values on the entire boundary of the region. So it does here. So u of 0 and y, we know it's equal to 0. So 0 and y, in fact, we are talking about this boundary. U of a and y is equal to 0. So we are talking about this boundary. U of x and 0 is equal to 0. So we are talking about this boundary. So in fact, in this problem, here is 0, here is 0, here is 0, and u of x and b is equal to fx. So we are talking about this boundary. Here it's fx. In fact, on any boundary of the region, so we have a prescribed value. I just want to clarify something. So for example, when I say here it's 0, here it's 0, here it's 0, or here is fx, so what does it mean? Let's say I'm talking about a one heat equation. Imagine I have one plate. It's a plate. So if I say that in this boundary temperature function is equal to 0, so it means that temperature on this edge of the plate is equal to 0, or temperature at this edge of the plate is equal to 0, or temperature at this edge of the plate is equal to 0. Or when I say here this edge temperature is the fx, for example, let's say fx is equal to sine x, for example, just an example. So it means that temperature at the edge is equal to 0, then it increases, then it decreases, increases. So I'm just talking about temperature at this edge. So the boundary condition at this edge is shown by fx. So it's definition of Dirichlet problems, and we have a maximum principle for Dirichlet problems. So based on this principle, a solution of Laplace equation within a bounded region R takes its maximum and minimum values on the boundaries. So as a result, if I give you one Laplace equation and I ask you, okay, so where is the maximum and minimum values of your function, so without solving the problem, you can say that it happens on the boundaries. It's about Dirichlet problem. Now we want to talk about superposition principle. So far we solved heat equation, wave equation, and Laplace equation, but all of them were homogeneous. If you have non-homogeneous problem, what happens? So a Dirichlet problem for a rectangle can be solved by separation of variable when homogeneous boundary conditions are specified on two parallel boundaries. However, the method of separation of variables is not applicable to Dirichlet problem when the boundary conditions on four sides of the rectangle are non-homogeneous. For example, if you look at this boundary value problem, so you can see that the first boundary condition says that u of 0 and y is equal to fy, so it's not homogeneous. The second one, u of a and y is equal to gy, non-homogeneous. Third one is u of x and 0 equal to hx, non-homogeneous, and the last one is non-homogeneous as well. So in fact, now in the boundary conditions on the two parallel boundaries, they are non-homogeneous. As a result, we cannot use separation of variable to solve this type of problems. In order to use separation of variables, so you have to manipulate these boundary value problems. In fact, if you have one equation like this, or one boundary value problem like this, that 4 or maybe 3 boundary conditions are non-homogeneous, so what you have to do, you have to make 2 problems. The first problem is problem number 1. So we assume that u1 of x at x, or second derivative of u1 with respect to x, plus second derivative of u1 with respect to y, it's equal to 0 for x between a and b, sorry, between 0 and a, and y between 0 and b. And so the boundary conditions that we have, so we assume that u of 0 and y is equal to 0, u of a and y is equal to 0, it's u1, and u1 of x and 0 is equal to hx, and u1 of x and b is equal px. Now we have one boundary value problem that we have 2 homogeneous boundary conditions on parallel edge, or on parallel boundaries. So you know what does parallel boundaries mean? For example, you know the region that you want to solve this problem, so it's x is between 0 and a, so here to here, and y is between 0 and b, here to here. That's why we are solving the problem in this region. So in fact, this region, this boundary is parallel with this boundary. What's this boundary? So it's u of x and b. Here we have u of x and 0, and this boundary is in parallel with this boundary. So here is u of 0 and y. Here we have u of a and y. So when we talk about parallel boundaries, so we are talking about these boundaries, this one and this one, or this one and this one. So it's problem number 1. In problem number 2, we solve this boundary value problem. So we assume that we have the same partial differential equation. Second derivative of here, I have u2 with respect to x, plus second derivative of u2 with respect to y, it's equal to 0. So again, x is between a and 0, y is between, sorry, x is between 0 and a, y is between 0 and b. And for boundary conditions, we assume that u2 of y, 0 and y is equal to fy, u2 of a and y is equal to gy, u2 of x and 0 is equal to 0, and u2 of x and b is equal to 0. So in this boundary value problem, we can use separation of variable. Why? Because in these 2 parallel boundaries, we have homogeneous boundary condition. As a result, you can easily find problem number 1. You can find u1 of x and y. You can easily solve problem number 2. You can find u2 of x and y. For both problem number 1 and number 2, you can use separation of variable and you can solve it. But you know, our goal is to find solution of this boundary value problem. We assume that solution of this boundary value problem is equal to u of x and y. It's equal to u1 of x and y plus u2 of x and y. Why this assumption is valid? Because u1 of x and y satisfies Laplace equation here. So you can see u2 of x and y satisfies Laplace equation. As a result, based on superposition principle, summation of u1 and u2 satisfies Laplace equation that you see here. So far we could satisfy partial differential equation. Now we want to check if the solution satisfies boundary condition of our boundary value problem or not. So we start with the first boundary condition. We have u of 0 and y is equal to u1 of 0 and y plus u2 of 0 and y. So here you can see u1 of 0 and y is equal to 0. u2 of 0 and y is here, so it's equal to fy. So it's fy, and 0 plus fy is equal to fy. So now you can see that u0 and 0 and y is equal to fy. Here we have fy. As a result, this boundary condition is satisfied. Let's go through the other boundary condition. So you have u of a and y, it's equal to u1 of a and y plus u2 of a and y. u1 of a and y, you can see here, it's equal to 0. u2 of a and y, you can see here, it's gy. So summation is equal to gy. So this boundary condition is satisfied. The third one says that u of x and 0 is equal to u1 of x and 0 plus u2 of x and 0. u1 of x and 0 is equal to hx. u2 of x and 0 is equal to 0, so it's equal to hx. So as a result, this boundary condition is satisfied, and u of x and b is equal to u1 of x and b plus u2 of x and b. So it's equal to u1 of x and b is equal to px. u2 of x and b is 0, so it's equal to px. As a result, this boundary condition is satisfied as well. Conclusion: if you have one boundary value problem that the boundary conditions on the two parallel boundaries are not equal to 0, they are non-homogeneous, so what you have to do, you have to split it in two problems, problem number 1, problem number 2, and in each problem you have to have homogeneous boundary condition at least on two parallel boundaries. Then you can easily solve u1, you can easily find u1 and you can easily find u2 using separation of variable. Then you have to add them together. U, which is summation of u1 and u2, is the solution of your original boundary value problems that you had.